In section 14.4, we're going to talk about regression models again, but this time we're going to examine how things fit, and we're going to say, hey, is there a model that would maybe fit better than a linear model? So here's the I can statement. I can determine what model is the best fit. So let's write the word fit right here, and the warm-up is just a review of some of the things that we've talked about this year, some of the different types of functions. So this one right here, you'll remember that this one is a piecewise, so I'm going to write piecewise. This next one, hopefully you recognize that. That's one of the main ones that we studied. This is exponential. Exponential. One of the other categories that we talked about is, hey, if you don't recognize it, just say that it's unfamiliar. Now, we've seen this shape before. It actually has a name, and you're going to study that in the next couple of years. It's called a quadratic. But for right now, this is not a shape we're very familiar with, so we're going to say it's unfamiliar. Unfamiliar. And then, of course, this last one is linear because it makes a line. Now, as we've talked about before, when we do a regression, what we're doing is we're starting off with the points and we're going backwards and we're trying to figure out what equation would have produced those points. Most of the time it's a linear equation because most of the time they line up and make a relatively straight line. They've got some linear pattern to them. But we're going backwards and we're finding that equation. Now, the calculator uses some really complicated and tedious math in order to figure out what that line of best fit, but that doesn't mean that the calculator is right. And what we're going to do in order to establish that is we're going to take a look at a familiar example. So I'm going to slide down here and we're going to look at example number 1. And it says, find your answers to numbers 24 through 27 on worksheet 14.2 to help with answering the questions below. So this data should look familiar. I'm going to go ahead and pull up 14.2 right now. So this is 24 through, let me slide down here so we can see 27 also. So this is that hot coffee problem where it was brewed at 186 degrees, and if they serve it too quickly and it spills, it might burn somebody. So on number 24, we were given this data, so just 2 pieces of data. Then we were asked to figure out a linear regression model, and here's what we come up with from this data right here. And if you do this on your calculator, you actually get an R value of -1. So the equation is y equals -7x plus 186. Remember, we do need to know what the y-intercept and the slope represent on a problem, especially in a real-world problem. And then R is -1. So I'm going to come back here and we're going to write those down. So again, the linear model is y equals -7x plus 186. The R value in this particular case was -1, and it says, is this correlation 0, weak, moderate, strong, or perfect? Well, it happens to be perfect. When you throw that in the calculator, it ends up being perfect. Well, what might some of our concerns be about this? When we did this problem originally, we said, hey, do you have any issues with this? So one thing might be we only have 2 pieces of data. So only 2 pieces of data. Okay, that might be one of them. Okay. Another one might be, this is perfect. So let's say perfect correlation. Perfect correlation, question mark. That almost never happens. It seldom or never happens. And if that's the case, we might be a little bit suspicious that there's something else going on here. And then the other thing we might notice is, hey, if this continues to cool off, remember this is losing 7 degrees of temperature every single minute. It starts off at 186 at time equals 0, and then every single minute it's losing 7 degrees. Well, it wouldn't take long before this coffee's freezing. Okay, so we'll say something like this. Does this pattern continue? Meaning, does this continue? Does this continue to lose 7 degrees every single minute? Well, the next example is actually hopefully going to answer some of these questions and maybe introduce some new questions that we might have. So if you take a look here, this is what we've got. We've got the same brewing data, so same coffee starts off at 186 degrees, and this is that next point. It lost 7 degrees in that first minute or so. But here's the rest of the story. This is keeping track of the temperature of this coffee for 23 minutes, and we hit minute 1, minute 2, minute 3, and then about every 5 minutes after that. Well, if you come over here and take a look at the scatter plot, this is what the scatter plot looks like. Now again, so whoever did this knows what they're doing. it's scaled in both directions. It's labeled. These may not be the most convenient scales on the temperature axis, but they'll certainly work. So it says, what do you notice about the graph now that we have more data? Well, when we had two pieces of data, we were just basically connecting these 2 points, so we'd get a line that looks something like this. Well, now that we've got more data, the first thing that jumps out at you is, hey, this isn't really a line, this is starting to curve. So let's just write down that this is curved. Okay, so it's curved. What type of function does this most look like? Well, if you remember up above, we were talking about piecewise and exponential and something called a quadratic, which was fairly unfamiliar to us right now, and a linear. Well, this does not look like a linear graph. So for the most part, I would say that this looks like an exponential. Exponential, okay? Now it says do a linear regression on your calculator, record the equation, the R value, and then graph the line and the scatter plot on the same set of axes. So here's what I'm going to do. I'm going to pull up, I've got a TI-83 right here, and I'm going to go ahead and turn this on. And I took the liberty of going ahead and putting in all that data there. Now I've got it in L1 and L2. I've got some other stuff in L3. But you'll notice if I come down here, I can double check all of these. I've got 23 and 129. I've got it all in there. Now, before I got on screen here, I made sure that every single one of these was right. So I'm going to go ahead and hit second quit, and I'm going to do a linear regression. So I'm going to hit stat. I'm going to hit calculate. I'm going to do number 4. Okay, so come down here and hit number 4, or it comes up this way. Now, automatically it's going to do a linear regression with L1 and L2. So it's going to give me this, and I get this, these values right here. So I get A, remember A is the slope, they use an A rather than an M. So this is negative 2.412, so we're going to say negative 2.41. And then the y-intercept is 180.134, so we're going to do 180.13. So I'm going to go ahead and shrink this down just a little bit so I can see both of those at the same time. And then I'm going to write down the equation. So we get y equals, this is negative 2.41x plus 180.13. It says record the R value. Now, if you take a look right here, we don't have the R value. I reset this calculator a little while ago, so I need to make this show the R values here. I need to make it show the correlation coefficient. So if you'll remember, we do that by turning on the diagnostics. Catalog is above the 0, so I'm going to hit second and catalog. Notice that the A is already highlighted, so if I want to go to the D's, all I need to do is find the letter D here, which is above the x to the negative 1 key. This is the same as if it were TI-84, so I'm going to hit that, and then I'm just going to come down here, diagnostics on, hit enter, and there we go. Now, I am going to, I'm going to clear this off, and I am going to recall this linear regression. Remember, it automatically does it with L1 and L2. So you'll notice that I get the same A, same slope here, and I get the same y-intercept here. Now again, this would be the predicted temperature if it hadn't cooled at all. Okay, so no minutes of cooling. And then the negative 2.41 means it's going to lose about 2.41 degrees every single minute, as opposed to that last one up above where it was 7 degrees every minute. So we can automatically see that this is very, very different. Now, on this linear regression, we get a 0.983. So again, we'll go to 2 decimal places. We'll call this negative 0.98. So negative 0.98. So we've got everything that they asked for there except for graphing this. So I'm going to come back here, and I'm going to put this in y equals. So I'm going to go ahead and put that line in there. Negative 2.41. We'll put an x. And then we plus 180.13. Again, double check and make sure that we've got that in there the right way. Now, some of you may know that there is actually a way to make the calculator store the regression equation in there with all the ugly decimal accuracy and stuff like that. We're not going to worry about that right now. If you know how to do that on an 83 or on an 84, you're welcome to do that. But we do want to go with these 2 decimal places of accuracy just for right now, just to make things a little bit cleaner. All right, so I'm going to go to stat plot. I'm going to turn this on. So hit enter. I've got the stat plot. I've got L1 and L2. We're all set there. Let's set up the window. Now the window, let's set it up like this. Let's only go from 0 to 25 in the X direction because we really don't need it that big. And then let's go from maybe, let's see, the smallest amount is 1. Let's go 120 up to about 190. So we'll put a tick mark every 5 in the x direction, and then we'll go from 120 to 190, and we'll put a tick mark about every 10. Now what that's going to do is that's going to kind of zoom in on this little area right here and see how good this looks. Now this is going to graph the scatter plot and the line on the same one. So let's see how this ends up looking. All right, so there we go. So not too bad. So you can see this curve right here. So it starts off right here, goes through this point, this point, this point, this point. Okay, but we've got this line that's making this prediction right here. So it actually only hits this point right here and this point right here, but really it's not too bad. Now, here's what we want to point out next. Since this has a bend in it, we should probably try a different regression. So we're not going to do a ton of these. The focus of this course is doing linear regressions. So we're going to do what's called an exponential regression. So we're going to hit Stat and Calculate, and we're going to find 0. So that's going to be an exponential regression model. So let's just write exponential right here. So exponential. All right. So here's how we do that. I'm going to hit second quit, and we're going to go to Stat. We're going to calculate, and the same thing is true on an 84. Now, if you want to go down, you're welcome to. I'm actually going to go up because it's a little bit quicker way to do this, or you could just hit the 0. So this is 0 exponential regression. So we're going to go ahead and hit enter. That's going to go to the home screen. By default, it's going to use L1 and L2 as the two lists. L1 is the X list, L2 is the Y list. So we're going to go ahead and hit enter. And takes a little while, but here's what it comes up with. So first thing we want to do is let's write down the equation. So A is this coefficient out in front. So this is going to be y equals 180.77, and that's rounded the right way. And then B is the base. So we're going to do in parentheses, this is going to be 0.98. That's not enough to bump it up. So we're going to do 0.98. And I'm going to do a little more decimal accuracy here. So let's just do 45, okay? Because this is going to make a fairly large difference there. And again, doing exponential regression equations is not the focus of this course. We're only going to do this one, I think. But then we're going to write down the R value. So the R value is, take a look at this, negative 0.99. So looking at this linear regression model, it had an R value, a correlation coefficient of negative 0.98. And this exponential regression model has a correlation coefficient of negative 0.99. So this is just a little bit better, a little closer fit here. So then we want to graph the curve and the scatter plot on the same set of axes. Now it doesn't say actually graph this, but we just want to see what it looks like. So we're going to go back to y equals, and I'm going to change this to this new one right here. Now if we wanted to, I'm just going to turn this one off. And I'm going to come on, let's see, y2, and I'm going to do 180.77, and then in parentheses, 0.9845, close the parentheses, and we're going to raise that to the x. And again, if you've got an 80, sorry, let's see, we've got to get the caret key there. If you've got an 84, these older calculators don't have what we call pretty print, so it doesn't look quite as nice. So there's that coefficient in front, 180.77. There's the base, 0.9845, so we're in good shape there. And then we raise this to the x power. If yours looks like an exponent, then that's great. So here's what we want to look at. I'm just going to go ahead and hit graph. And this doesn't look like much of a curve, but it does look like it's a little bit curved, and it does look like it's a little bit better fit. Even though it only goes through that one point specifically, it does look like it's closer overall than the other one. Now, just for the heck of it, I'm going to come back here, and we're going to go to y equals, and I'm going to turn the other one back on. So now what we've got is we've got the original data in the plot, we've got a linear model in y1, and we've got an exponential model in y2. So let's just take a look at this and see how it looks. Yeah, so not too bad. I mean, either one of them are really good as indicated by the correlation coefficients. But what we're going to say here is I'm going to go ahead and make this full screen here. We're going to say that, of the two, I mean, if we just flat had to choose, we'd probably choose the one that has the highest correlation coefficient, the strongest correlation. So we're going to say which regression model gives the better fit to the data, and we're going to say it's the exponential one, okay? Or we could just say exponential, okay? All right, let's take a look at the next page. Okay, on this back side, we're ready to take a look at this coffee cooling problem with all the data and all of the information. So you'll notice over here on the scatter plot that's scaled and labeled just like it was before, I've got a whole bunch more information. In fact, this data was tracked all the way out to 2 hours, 120 minutes. So they did it at 0 minutes, right at the initial time. It started off at 186 degrees. After 1 minute, it was 179, 2 minutes, 3 minutes, and then 8, 13, and so forth. They basically went about every 5 minutes for the first hour, and then they did it about every 10 minutes to a half hour, 20 minutes after that. So we've got a whole bunch of data here, and you'll notice what happens is not only is this curved, but it's curved just like an exponential, and it comes out here, and it kind of levels off. Which should make sense, because if we had that first linear model that was going from 186 to 179 and went like this, we'd end up having freezing temperatures. I mean, the coffee would be freezing in a very short amount of time, and that doesn't seem very realistic. Okay, so the first thing we notice about this and why an exponential model might be better than a linear model is it can do some things that a linear model cannot do. So the first thing is that the exponential model, the graph can curve. Okay, so let's write that down, that it can curve. Okay, so that's the first benefit to using an exponential model, is it's able to curve. And then the next thing is the curve can have an exponential model can have an asymptote. Okay, so what's going to happen is it's going to come out here and it's going to cool off, and I'll give you the whole story here. Remember, it's got a room temperature of 71 degrees. It wouldn't make any sense for coffee that's in a room that's 71 degrees for it to get any cooler than 71 degrees. So it's going to come out here and it's going to level off at 71 degrees, and that's going to be our asymptote. It would be y equals, or t equals 71 degrees. Now, when we were talking about this before in Unit 4.2, you'll remember that the woman that sued McDonald's, they were serving coffee at a temperature at 180 degrees. And the result of all of that lawsuit and everything is, because of the expert testimony and all, they figured out that, if you served coffee, and most people like coffee hot, if you serve it about 155 degrees, that's hot enough to keep people happy. But if you were to spill it on your blouse or your pant leg or something like that, unless it's on bare skin, it's not going to burn it instantly. You've got a little bit more time. Now, it would still be hot. It might be uncomfortable and stuff like that. But if you serve it at 155 degrees, that's a relatively safe temperature. So if we go back and look at, I don't think it's number 31, but we're going to go back and take a look at this right here. If we look at this one right here on number 26, it says figure out how long it would take it to get it down to 55 degrees. Well, it takes it a little bit more than 4 minutes. Okay, so on this one here, we're going to say it takes a little bit more than 4 minutes. Now, with all of this data together, we can now figure out, hey, that's probably not a very good prediction. It's not going to cool that quickly. We can look at this data and we can figure out how long it's actually going to be how long it's going to be before it's safe to serve. So it needs to get down to 155 degrees. Well, we could look over here. 155 would be about right here, but it's really tough to tell on the scatter plot, but we can come over to the data. Take a look at this. It's going from 186, we're down to 175. At 8 minutes, it's at 156. So if we let a little bit more than 8 minutes going to go by, it's going to hit that 155 degrees. So it's going to take a little bit more than 8 minutes. Now, if you think about the difference between the two of these, the linear model would predict about 4 minutes. The exponential model would predict about 8 minutes. That's a big difference. Okay, quite a bit of time to wait for that to cool off completely. Now that we've kind of wrapped up this discussion about cooling problems, I want to make a really important note, and that is that linear and exponential regression models are almost never perfect. They very seldom fit all of the data perfectly because it's real-world data. In fact, if we were going to fit this curve perfectly or figure out what the exact formula was for this cooling, we'd have to do some really advanced mathematics, we'd have to do some transformations, some really fancy regression stuff with exponentials, and we'd arrive at something called Newton's law of cooling. Okay? Really, I'm not sure he invented it, and mathematicians have a tendency to name things after people who just made them popular rather than discovered them. But that would be Newton's law of cooling, and we'd have to do some advanced stuff to get there. So let's take a look at this next example here, and it says, use the data and what you know about scatter plots and regression equations to find the answer to the following question. So we've got some data right here. This is about sandwiches, how many fat grams they have, and how many total calories. And it says, will a linear or exponential model fit the data best? So I'm going to pull up the calculator. I've got this stuff in my 84 already. So I'm going to go ahead and take a look at this. So we've got in L1 and L2, whoops, actually I've got this in L3 and L4. So there's the 9 and the 260. I've got a 34 and a 590 if I go all the way down to the bottom. Let's see, there's our 5 grams of fat and 300 calories altogether. Now, I'm going to do something that I've shown you once before, but I want to see if we can do this again. What I'd like to do, by default, the calculator works a little better with L1 and L2. So if I've got L3 with the X's and I want to transfer those over here, you'll notice that this is that coffee cooling data. I'm just going to get on top of L1, I'm going to highlight that, and I'm going to hit second. And then right above the 3 is L3, so I hit that. So what we're doing here is saying L1 is equal to L3. So if I hit enter, watch what happens. It copies L3 all the way over there. And then I'm going to do the same with L4 and L2. I'm going to put L4 right here in L2. So I'm going to be on top of L2. I'm going to hit second, and here's above 4 is L4. So I'm going to make L4 equal to L2, or vice versa if you want to say it that way. Hit enter. Now if I slide over here, you can see that those are the same. Now I don't need L3 and L4 anymore, so I'm going to go ahead and clear those off just to clean this up a little bit and avoid any confusion. Again, we clear lists, we don't delete them. Okay, so now I'm all set to go. So I'm going to do two things. I'm going to do a linear regression and I'm going to do an exponential regression. So I'm going to hit second quit. And let's see, we're going to hit stat. We're going to calculate. I'm going to do a linear regression. That's number 4. I'm on an 84 this time, so you'll notice it has L1 and L2. We don't need a frequency list. This is where you could store the regression equation in Y1, but I'll show you how to do that another time. We're going to come down here and we're going to do calculate. One thing you could do is you can just keep hitting enter, and it'll get down there, and here we are. So there is our linear regression model. So we've got, and I'm going to make this smaller so we can write it down. So we start off with a y-intercept of 193.85. Okay, so I'm going to write down y equals, and this is 11.73, so 11.73x, and then plus 193.85. Yep, neither of those round. And I'm going to write r equals 0.97. So this tells us there's a positive relationship, pretty strong positive relationship. And we can see that the sign of the correlation coefficient and the sign of the slope are exactly the same. Now, with the exact same data, I'm going to come back here and we're going to hit stat and calculate. Again, I could hit the 0 or I could hit the up arrow. That's probably the quickest way to get there just to make sure we're seeing the right thing. And notice that it says L1, L2. We've got exponential regression highlighted up there. Come down here, hit enter, and it does the calculation for us. So here's what we've got, that coefficient out front. So I'm going to write y equals 232.86. Remember, we're going to round that. Then b, the base of the exponential, I'm going to do 1.0289. We'll go 4 decimal places on that. We raise that to the x, and we get r equals this is going to be 0.96, but that rounds up, so this is going to be 0.96, I'd say 0.97, but I'm going to put that on there just in case. Now, we've got a bit of a tie if we were to round, and I just want to go back and double check this. So I'm going to hit second enter and second enter. So it's going to do a linear regression. You can see that right there. And it's 974, so I'm going to put a 4 right here, okay, just to make sure we're good. So I think the linear regression model is going to work a little bit better for this, and the reason for that is larger R value, larger correlation coefficient, okay? So there's our explanation. Now we could, if we wanted to, we could plot the data and see how it looks. But we're going to go with the linear model because that's what we do most of the time in this class. Okay, so let's take a look at here. It says write the equation that best fits the data. So we've got that one here. I'm going to go ahead and write down y equals 11.73x plus 193.85. And what is the correlation coefficient, and what does it mean about the regression equation? So the correlation coefficient that we're using is the 0.974, and we're going to say this. What it means is a strong positive correlation. Strong positive correlation. So that means it should be pretty good at making predictions. So it says predict the total calories if the sandwich has 26 grams of fat, and show your work. So we're going to do y equals, this is going to be 11.73 times, let's see, 26 grams of fat. Remember, fat is the x value. So we're going to put 26 right here, and then we're going to add 193.85. So I'm going to hit second quit. Whoops, second quit. There we go. Clear everything off. We're going to do 11.73 times 26, and then we're going to add 193.85. So make sure we've got it all typed in there the right way. That looks good. So we get 498.83. So we're going to say it's 498.83 calories. Okay, so there's the answer on that one. Okay, and then it says predict the number of fat grams if the total calories in a sandwich is 280. So they're telling us calories on this one, and they want us to predict fat grams, whereas this one, they told us fat grams and they wanted us to predict calories. So we're basically doing the exact opposite. So where they gave us the x value on this one, the independent variable, so to speak, here they gave us the y value, or the dependent variable. So we're going to do 280 equals 11.73x plus 193.85. So then we're going to subtract 193.85. So I'll do 280 minus 193.85. Okay, so we got that. So 86.15. So 86.15 equals that other side, which is 11.73x. And then we're just going to divide by 11.73. So 11.73. So divide that by 11.73. Make sure I typed everything in right. And I get 7.34. So x is equal to 7.34. Now, that's an x value, so this is going to be 7.34 grams, or we'll say fat grams. Okay, and then we'll circle that. Okay, do the predictions above seem reasonable, and make an explanation. So let's check. Does this one seem reasonable right here? So I'm going to go ahead and go full screen on this one. They said if we've got 26 grams of fat in a sandwich, does that seem like a reasonable prediction of 498 calories, almost 499 calories? Well, let's find one over here that has about that many calories, okay? Well, there's one with 25 and it has about 500. We've got 26 and it's right about 500. Now, there's always a little bit of variability here, so that looks like a pretty good estimate, so not bad on that one. And then let's take a look at this one, 280 calories, and we're predicting about 7 grams of fat. So let's see if there's one that's around 280. So here's one that's 260, and there's 9 grams of fat. That's a little bit more than what we would expect based off our prediction. Here's one that's 300, and there's 5. So let's see, 260 and 9 and 305. So if we had about 280, somewhere in between those, we would expect, so somewhere in between these two calories should be somewhere in between those two as far as fat grams. Maybe that kind of makes sense, and we're at about 7. So yeah, that makes some pretty good sense. So I'm going to shrink this down just a little bit. And we're going to say something like this. So, do the predictions made above seem reasonable? Yes. And our explanation is they fit the data pattern. They fit the data pattern. Now, if we were to go through and we were to actually graph this with a scatter plot and everything, we might be able to see that, hey, gosh, those line up pretty well. Everything looks great. In fact, let's go ahead and do that really quickly. We've got the data in the calculator already, so let's go ahead and take a look. So we're going to do, let's see, we've got in y equals, we're going to put that 11.73, so 11.73x, and then plus 193.85. Okay, so we've got that. And let's check our stat plot here. It's on, it's L1 and it's L2. Let's see what our window is. 0 to 25. Okay, let's see, we need the right number of calories. So we need to be, let's see, let's make this about, let's see, 35. 35 will probably do it. I think that's the most. And then in the in the y direction, let's go from the smallest one, let's say about 200 up to, I don't think any of them are above 600. So let's go 200 to 600. And we'll do a tick mark about every 50. Okay, so we'll graph that. And gosh, that looks pretty good. And if we were to do, let's say, 26 fat grams, so I'm going to hit trace, and I'm going to hop on the line, and we're going to do 26 fat grams. So we're going to go to 26. It's right there on the line. That's what it would predict. There's our 498.83, and it looks like it's right in that linear pattern there. And then if we were going to go to 280 calories, let's see how close we can get to this. We're coming down here. We're looking at the y, not the x's. So we're going to come down here. We're going to get to 280 calories. Get as close as we can. And let's see. Okay, that's about as close as we can get right there. Okay, so there's ours, about 7.34, 7.44 is what we predict right here. But again, it's right in there with the linear pattern. Okay, so hopefully that helps out a lot. We're hopefully getting a really good understanding of how these regression models work. And that sometimes a linear model is maybe not the best one to use. We're going to focus on linear models for this class, but if you do take a more advanced statistics course or something like that, then you're going to probably run into other types of models that would work a little bit better. So go ahead and do the self-assessment, and then you've got a pretty short assignment today, so good luck on that.